Okay, we're gonna continue on here, chapter two, and then, like I said, we're going to go off to chapter 10 afterwards. Chapter three has already been up there posted, so make sure again you watch it. So last time we kind of finished up talking about. So last time we talked about really conversions, conversion factor, equalities, dimensional analysis. So remember when we say kind of show your work here in chemistry, it really is dimensional analysis. Again, that is the setup as we did in a lot of those problems where we basically show the units canceling as conversion factors. Remember to cancel out units. We basically go opposites. So again, you want to always kind of put the unit you want to get rid of in the opposite location of what you want. And again, when we set it up like this, all we're doing is multiplying on the top. We're dividing on the bottom, and that will get us what we need. These will cancel, and it'll leave us with unit C, for example. So remember that if you're looking for just sort of one unit at the end, that unit should be up there on top. Again, if you're looking for multiple units, you got to make sure everybody's in the right location. As I talked about last time, one of the nice things about this is if you sort of set it up like this, which you should, it oftentimes will take care of sort of any type of formula sometimes and not worrying about, am I doing the right math or not? Because again, all you're doing here is anything on top is going to be multiplied, anything on the bottom is going to be divided. It keeps everything very sort of simple in terms of the math part of it, no kind of rearranging formulas and stuff like that. So even as we go through different chapters, but you could kind of solve a lot of problems through dimensional analysis, really just looking at the units and just thinking about what units you want to get rid of, what units you want to end up with. And a lot of times it can help you even if you don't really know the formula or not really sure what the formula is. Just kind of set up the units so that they cancel out and you're left with whatever you're looking for. A lot of times you can almost solve a number of problems dimensional analysis way without necessarily having to plug or chug sort of into a formula. Any questions on any of that stuff there? Okay, so let's say we were driving, for example, 65.5 miles per hour. We want to know, how many kilometers per minute that would be, right? So why don't you give that a go and give you some maybe conversions that might be helpful for you. Um, 1 kilometer is 0.621 miles. And then obviously, hopefully, the time sort of aspect of it. So why don't you give that one a go? Why don't you also do, if we had, let's go with 45.5 cubic centimeters. How many cubic feet would that be? So 1 inch is 2.54 centimeters. 12 inches in a foot, hopefully, All right, so I want you to take a few moments and do both of those. I'll do it as well because I just made it. Okay, so let's take a look, see how you're doing. So we'll start with the first one here. We're driving 65.5 miles per hour. Remember, when you see something per something, as we talked about last time, that's essentially a fraction. So we basically have 65.5 miles over an hour. And usually the number stays with the first thing, and the per thing is one basically on the bottom. And again, it's really important to set this up in dimensional analysis way and setting it up exactly sort of like that you could clearly see the miles are on top and you can clearly see that hours are on the bottom. Not like a lot of people will kind of write it like this, miles an hour, and they're not really sure, what's on top, what's on the bottom, and stuff like that. So it's really important to make sure as you kind of do that because it's going to help with the sort of math part of it and the dimensional analysis part of it to do it correctly. So really, when you think about it, we really have two units that we need to convert. We need to take the miles, which again are on top, to kilometers, and we need to take the hours, which are on the bottom, to minutes. And again, keeping it sort of separated like that through dimensional analysis allows you to easily do hopefully the correct math. Now, in this case, it doesn't really matter which one you start with. You can either do the miles to the kilometers, you can do the hours to the minutes first. It doesn't really matter. But having it set up like that will allow you to, again, keep it separate. So here I'm going to go miles to kilometers first. In this case, we have an equality here that will allow us to do a direct conversion to it. And by setting it up like this, once again, we want to go opposites cancel. So miles are up on top, which means when we use this equality as a conversion factor, we would need to put the miles on the bottom, and that would give us the 1 kilometer up on top. At this point, if we stop the calculation, our miles would cancel, and we actually would be in units of kilometers per hour, which actually means we're pretty good there. We got the top part actually done there in one little conversion. Now, again, setting it up like this, we can now very much also clearly see that our units of hours, which we want to get rid of next, is on the bottom. And that's going to tell us that if we need to get rid of hours, we got to go opposite. So we got to put that up on top. And again, hopefully we know this conversion, right? 1 hour would go on top, and that would give us 60 minutes. Hours on top and bottom will cancel. We have now hit kilometers per minute, which is actually what we're looking for. The reason to set it up like this, besides as we've been talking about, you're supposed to set it up like this, is it will now take care of really all the math correctly for you. Once again, anything on top gets multiplied, and everything here on the bottom gets divided. So you don't have to think about multiplying or dividing it correctly. It should be set up for you. We'll take our 65.5. There's really nothing to multiply on top. Divided by 0.621, divided by 60 in this case, will give us on our calculator here 1.757917,338. Units again are kilometers per minute. Again, the number stays with the top unit, bottom unit is 1. Here we do have to look at significant figures. We don't have to worry about that as that's an exact conversion. Should I worry about this one? The answer is yes. And here we should look at this is again a metric to English conversion. This has 3 significant figures. Our original number there has 3 significant figures. That means since we're only multiplying and dividing when we do dimensional analysis, 3 significant figures is a winner. That is a 7, which means we got to do a little rounding there up on that guy. And that's going to give us a 1.76 kilometers per minute in this case. Any questions on that or the setup? Again, doing it this way is really helpful. Again, cannot tell you how many people will multiply that 60 at the end instead of divide in this situation. And again, it's because they don't set it up that they can see the units. So by doing this, it really helps a lot with the math. It helps a lot with seeing, where things should go and how you should use the conversion factors correctly. Any questions on that particular one there? All right, so let's take a look at the bottom one here. And the bottom one, we have 45.5 cubic centimeters. And we want to get to cubic feet. So we can use centimeters, for example, to inches. And once we have it in inches, we could go to feet at that point. So when we do this, the first thing we're going to do again is opposites. So we'll use our conversion factor here, 2.54 centimeters on the bottom, 1 inch on top. Now, this is actually cubed, correct? So did I cancel out all the cubedness there of my centimeters? I did not. I only took care of one of them. So really, in this case, you would need to do this conversion not once, not twice, but you would need to do it 3 times. And in this case, centimeters, centimeters, centimeters is centimeters cubed, which would completely cancel this out. The units I'm in at this point, if I stopped, is now inches cubed, right? Inches times inches up there on top would give me my inches cubed. And again, we could see here that the inches are on top, so we could use our next conversion factor to get rid of the inches. And in this case, we would have 12 inches is 1 foot. Once again, we would need to do this one 3 times here. So good thing you didn't need to do it 4 times. I ran out of room there. So inches, inches, inches are cubic inches. Takes care of the inches, inches, inches. And now we are left with feet cubed, which is what we want. Yeah. You can. We're going to talk about it in 1 second, and you absolutely could do that. And I'll talk about it in 1 second as soon as we're done here. Yeah. So at this point, we're left here again, multiplying what's on top and dividing by what's on the bottom. So 45.5, if I punch it in right, 45.5, that's all ones basically up on top. Here again is a situation, if you're dividing everything on the bottom, I would use that equal sign multiple times. So I would divide by 2.54, hit equals, divide by 2.54, hit equals, divide by 2.54, hit equals, divide by 12, hit equals, divide by 12, hit equals, and divide by 12, hit equals. And that's going to get you here 0.001606.817 cubic feet. Significant figure-wise, remember, this is considered an exact conversion, so we don't have to worry about it. That's an exact conversion. So here we would go back to our original number that has 3 significant figures. That would take us to here, which means we actually do need to round up again in this situation. And 161 looks like cubic feet. First off, any questions on that calculation there? So I did want to show these two for 2 reasons. Sometimes people get a little confused when there's 2 different units you got to change. You could just think of them as separate conversions, just do them individually. As long as you set it up dimensional analysis way, top and bottom, that will keep everything separated correctly. And this is also a very common mistake that people make, which is they don't do the cubing part right. So to answer your question, could you do this basically 45.5 cubic centimeters? 1 inch is 2.54 centimeters cubed, and 12 inches is 1 foot cubed. Right, that's basically your question? Yeah. Yeah, so you absolutely can. I don't, if you do it, it's perfectly fine. You'll get credit. There's really nothing wrong with it. But I will tell you that in my experience, I don't know how many papers I've seen where people set it up like this and they never live to actually cube the number. They just do the units part and they forget about, like, I actually got to do the number 3 times. So it's perfectly fine as long as you remember to actually do the math correctly. But sometimes, just writing it out like that, it'll remind you, oh, I got to do like the 2.54 3 times. But it's super common error that people will do it like this, which is perfectly correct setup wise. It's absolutely correct. But they kind of failed to do the math correctly part of it. So you could absolutely do it this way. It's perfectly fine. Just don't forget to do the math part. It's super, super common thing. People always like do the units and never touch the number or do anything mathematically with the number. Other questions? All right, then let's finish up this chapter here as I scribbled on this page, apparently. Get rid of what I just put on this page. There we go. All right. So density, as we talked about in lab on Monday as well, is mass over volume. And obviously, as we talked about, the density of an object will kind of determine, for example, whether or not something will sink or float, for example, in water. Density is mass divided by volume. It is an equation, as we talked about, that you should think of it as an equation, and it is sort of rearranged and solved for any of those things. So volume is mass divided by density, and mass would be volume times density. Sometimes people remember the DMV triangle. Everybody loves the DMV, right? So a little bit like that. Density is mass divided by volume. Volume is mass over density, and mass is density times volume. So you can kind of use a DMV triangle if you like. Now, the typical units of density, as we see on the bottom there, we sort of talked about last time, is for solids and liquids, typically speaking, grams per milliliter or grams per cubic centimeter are going to be your standard unit. Again, a reminder that 1 milliliter is the same as a cubic centimeter. Remember that these both are volumes. And as we did in the lab there, you could either take a volume reading to get the volume. You could also, if you have a solid like our wooden cubes there, you can take some length measurements with a ruler and get the volume of it by doing a calculation as well. For gases, typically density is given in grams per liter if you are dealing with a gas. We won't deal too much with density of gases here in this class, but if you continue on to 1A, you'll talk a little bit about density of gases when you get to the gas chapter. And typically they're given in grams per liter. But for the most part for our class here, usually these are your kind of go-to units that we see for density. The density of water is an important value that people always want you to know, and you should know the density of water, and it is 1 gram per milliliter. And it does change with temperature. So the density of substance will change with temperature. But it is almost also a pretty safe bet, like I said, it's probably in lab, that if you come across a problem and for some reason you need the density of water and it's not given to you, using it as 1 gram per milliliter is usually a pretty safe bet to use it. But it does definitely change with temperature as well. Yeah. Yeah.
Figure it out. Does it matter which one we use, whether grams per milliliter or grams per centimeters cubed?
It technically doesn't in the sense that it is going to be the same number. So the number wouldn't change because it's a 1-to-1 conversion between milliliters and cubic centimeters. I would say in most cases, if you're dealing with something that's a volume, a liquid basically, or something like that, milliliters is usually used. And if something is a solid, sometimes cubic centimeters is used. But they are sort of interchangeable, and value-wise, it'll be the same because it's a 1-to-1 conversion between milliliters and cubic centimeters. Yeah. Now, obviously, if you did grams per liter, that would give you obviously a different number because liters and milliliters are 1,000-fold difference and stuff like that. Yeah. All right, so why don't we try one here? A block has a volume of 25.3 cubic centimeters, has a mass of 21.7. Okay, so let's take a look. And once again, in chemistry and in general, when you're dealing with problems, a lot of times it's a really good practice to kind of pull the information out of the problem, kind of label what it is. So obviously we have a volume here that is 25.3 cubic centimeters. We got a mass that is 21.7 grams. So obviously here that should point you to our density equation, and we're good to go on this one. Just to plug and chug into it, 21.7 grams divided by 25.3 cubic centimeters in this case, and that's going to get us here 0.8577071 on our calculator here. Again, significant figure wise, we are dividing, so we are looking at significant figures. So that is 3 significant figures there. That is 3 significant figures there. That means that we should go to 3 significant figures here on our answer. Once again, we would look at the next number, which is a 7. So we will be doing a little bit of rounding. If I write the number right there, 0.858 grams per cubic centimeter. Once again, here in terms of density, the number does stay with the grams part, and it is like 1 cubic centimeter on the bottom. Any questions on that one there? So again, we want to still remember to kind of look at significant figures, give our answers to the proper number of figures. Now, as we did in lab and as we talked about, There's kind of three ways that we could kind of get a volume when we're dealing with a lot of times density, for example. We can, as we talked about, and you did on Monday, just fill something up in a graduated cylinder and just take a straight volume reading. You could do a measurement like you did, length times width times height, which again, cubing that length measurement, going to give us a volume, in this case of cubic centimeters. The third way, like we did in part 2 of that experiment, is volume by displacement. So the idea of volume by displacement, as you saw and as we see here in this picture, is we could fill a container with some sort of liquid, like water, and we'll have an initial volume, and we could take an initial volume of that. We take a solid object like a person diving into the tank. The result of that is that object will displace water or a liquid that is equal to its own volume, and the volume level here will rise to a final volume. And to find the volume of an object, all you have to do is essentially just take the difference between the two volumes. So the volume of the object going to be our final volume minus our initial volume. And again, that's a very common and like kind of super easy way to figure out the volume of some type of solid object like we did with our stopper. You could also have done it with something like the block as well if you had a bigger beaker to put it in and stuff like that. Any questions on that there? All right, hopefully she'll get out of the tank. Hopefully those are stairs and not just markings as well. All right. All right, so let's give one a go here. Student fills graduated cylinder with 25 milliliters of a liquid. Then they immerse a solid into it. The volume goes to 33.9, and the mass of it is 63.5. What is the density? So take a few moments there and calculate. Okay, so let's take a look at this. Very similar to what we did. We have a graduated cylinder there. It has an initial volume there of 25 milliliters. We're going to take a solid that has a mass of 63.5 grams. We're going to drop it in there. And our volume here will go up to 33.9 milliliters. So again, we're looking for the density, which is mass over volume. We obviously have the mass given to us. This is our volume by displacement, so we need to find the volume of our object here. Once again, that is going to be final minus initial. So in this case, we'll take our 33.9 milliliters. We will subtract our initial volume of 25 milliliters. And that's going to get us there 33.9 minus 25, 8.9 milliliters. We now have the volume of the object that we need to go into our density equation. Density then would be 63.5 grams divided by 8.9 milliliters. And that's going to get us here. I don't think that's right. 63.5 divided by 8.9 here. It's going to give us 7.13 grams per milliliter in this case on our calculator, or 4.8, I guess, a couple other numbers. We do want to look at significant figure wise, and in this case, this is dividing, which is the last thing that we did, which was 3 significant figures. This guy actually has 2 significant figures, so 7.1 grams per milliliter is where we should end up with. And it's really based off of the volume calculation that we did back here. We are subtracting, which means we're going to decimal places, which is 1 decimal place. But remember that this answer with 1 decimal place gives us 2 significant figures, which is important when we do our last part of the calculation, which is dividing, where we're looking at significant figures. So again, really it's determined by the volume calculation here. Which again, we want to go to the proper number of decimal places, but again, gives us a certain number of significant figures. Any questions on that there? Okay. One last one here. Here's the density by way of some objects. And as you can see, we do have our liquid water, which is 1 gram per milliliter. And that again is one value that you should know. Here, 1.000 grams per cubic centimeter, you should know. Again, things that are heavier will sink, and obviously things that are lighter will float. If you're talking about two liquids, for example, that have different densities, and you put them into a, say, graduated cylinder, they would basically separate out as layers if they have different densities, right? The one with the highest density would be on the bottom, right? And the one with the smallest density will be towards the top, right? So if I put something in there and it just kind of floats right there in that layer, that means whatever I put in there is more dense than what's above it, right? Less dense than what is below it in that particular case as well when you look at it. By the way, again, most things in their solid state are more dense than their liquid state. One exception is ice, right? Which is water. Ice is actually less dense than liquid water. And that's why you put ice in your drink, right? It floats to the top, right? And that's because when water gets together in the solid phase, as we'll talk about, because of hydrogen bonding, they actually can't get super close to each other in a solid state. They don't have enough energy to really come right into each other. It actually creates a lot of open space between the different water molecules. And if you think about density, which is mass over volume, because these water molecules, when they freeze, have all this open space between them, the volume gets larger, and the volume gets larger, the density of ice gets smaller than it is in the liquid state. And that's one weird sort of property of water. Most things solid is much more dense than in the liquid state, but ice is an example of that, and water is an example of that because of when it comes together, it just can't get close enough to each other, and it creates all this really open void spaces between them, and it increases the volume, decreases the density in that case. Any questions on that there? All right, so again, here's some other densities along the way. One last example here, student needs 150 cubic centimeters of salt for an experiment. The density of salt is 2.16 grams per cubic centimeter. How many 1 pound boxes of salt would they need? And a reminder, a conversion that you should know, 1 pound is 453 points. Okay, so let's take a look. Once again, if we pull up the information, 150 cubic centimeters is a volume. In this case, we do have the density, which is 2.16 grams per cubic centimeter. And we want to know how many 1 pound boxes to go with. So obviously, if you know your density equation, which you do need to know, you got density, you got volume. So it would make sense. Mass is kind of the only thing you don't have. So you can use it to figure out the mass. That would obviously give us our mass in grams. And then from grams, you could figure out, for example, how many pound boxes you would need. Now, you could do this one of two ways. You obviously could plug and chug. You could rearrange the density equation. But let's just say, for example, as I was talking about earlier, where dimensional analysis is really helpful as well is, again, you might not even have to play with this equation and worry about maybe messing up rearranging or anything like that. So because we have the density, we could actually use the density as a conversion factor because frankly, it's a fraction. So we could flip it around like so and really use it in either direction as a conversion factor. And if we take a more dimensional analysis approach here, all we have to do is go, well, this is a volume and I want to end up with some type of mass, which is grams. So I'm just going to kind of dimensional analysis, which is all I have to remember is opposite. So that guy is opposite. So I'll just use it like that. And now without even thinking about the formula or rearranging the formula, I'm able to basically figure out the mass here by doing so. Yeah. Yeah. You don't have to do it with this one because the number that we have there, I'm assuming you're talking about the 150 cubic centimeters part, the 150 number. Uh, Yeah. We don't have to do it because this number is already been cubed, if that makes sense, to get to those units already. So it's already done that. The reason we don't have to worry about it here is the unit that's associated with the density is also already cubed as well. So because that's a cubic centimeter, which is a volume, it will perfectly cancel out with the cubic centimeter, which is the 150 cubic centimeters in this case. This wouldn't be the density in this example if you had, for example, grams per just 1 centimeter on the bottom. If you had something like 1 gram per 1 centimeter, then you would have to do it 3 times. But because the density unit's already in the proper unit, we're good to go on that one. Yeah. Other questions? All right, so we're going to multiply the top. And again, by doing it dimensional analysis way, I know mathematically what I'm supposed to do. I'm just supposed to multiply basically and divide. So in this case, we would multiply, and we would get something like 324 grams, which is really the mass here. And that is obviously the same thing you would get if you rearrange that equation and did this, but you didn't have to think about rearranging the equation. Basically, you just kind of take the dimensional analysis approach. It kind of does the rearranging for you. It also does the math part of it for you as well, in terms of I just got to multiply the top, divide the bottom, opposites cancel. So that's what I was saying earlier, that you kind of use dimensional analysis to your benefit in a lot of cases, especially if you're at a situation where you're maybe not sure of a formula or how to rearrange it properly. You can just keep it really simple, just try to get rid of the units you don't want, keep the units you do want, and a lot of times it'll get you there. Now, in terms of significant figures, we should really look at both of these numbers. So really this has 3 significant figures. This actually has 2 significant figures, which means really this guy should end up with 2 significant figures, which is 320 grams of salt. We also want to remember to also answer the question that it's really asking, which is, in this case, how many 1-pound boxes you need. In this case, we would just need 1 box, right? It would be sufficient. We'll have some left over and all that good stuff. So you want to make sure that you do answer the question in this case as well. Any questions on that there? All right. Questions on density, conversions, any of those things? All right, that should wrap up chapter 2. There it is. We're going to go off to chapter 3. Not 3. We're skipping 3, as I mentioned. Not skipping, but 3 is a recorded lecture. So again, 3 is up there for you to watch already. And we're going to go to chapter 10 next. And chapter 3, pre-recorded lecture, you are responsible for it. It is also basically the subject of, for us, the experiment we're doing on Monday. So again, I definitely would watch it before Monday, so you have a pretty good idea what's going on in terms of the experiment. And also will help you obviously with pre-lab assignments and stuff like that that's due on Sunday. Sunday for us. So we're going to go chapter 10, which is energy. This is going to be the last chapter for the first exam. Yeah, so this is going to be the last chapter. It's going to be part of the first exam here. So let's get into energy and a little bit about it. So when we talk about energy, which is sometimes an area of study which is related to what is referred to as thermodynamics in chemistry. And when you get to 1A, you'll talk more about energy, which is the first law of thermodynamics. And when you get to 1B, you'll talk about the second and third law of thermodynamics. But in this case, energy deals with whether or not, for example, a reaction is going to release a certain amount of energy, whether or not they're going to absorb a certain amount of energy as a result of that. And whenever we sort of talk about thermodynamics in general, there's kind of 2 things that we look at. We look at what's referred to as the system. The system is pretty much anything that you're dealing with. So for example, in the lab, if you're doing an experiment in a test tube, your test tube's your system. If you're doing it in a beaker, the beaker's your system. And the other part is pretty much what is referred to as the surroundings. So a lot of times we think about the system and the surroundings. And again, the system is anything you're kind of dealing with. The surroundings obviously is everything else around it. And in terms of energy, we're going to talk a lot about sort of the flow of energy. And in certain cases, we'll have a flow of energy going from the system to the surroundings. And in other cases, the surroundings may be supplying some energy to the system. So what we're going to be looking at here is energy. We'll do some energy calculations, kind of the flow of energy from one spot to the next. There's three type of systems that we come across. There's an open system, and in an open system, you can exchange mass and energy with the surroundings. So for example, if you had like a beaker, it's open on top, so you could take stuff in and out of the beaker, right? In terms of mass, it also can get hot or cold depending on what's going on in terms of the reaction. You could have a closed system where we still have transfer of energy, but maybe you can't take things out. So for example, if you had a flask, you put like a stopper in it. Can't get anything out of it because it's all stoppered up, right? No mass is going to be lost. Hopefully nothing through evaporation or anything like that. And in an isolated system, there's no transfer of either. So you can't take anything out mass-wise, and you basically have no energy being transferred from inside the system to the surroundings. So here's some examples of that. Again, in an open flask, you could take whatever in and out the mass. You also got heat exchange, put a stopper on it. Now it kind of prevents things from leaving, but you still have that heat exchange. And in an isolated system, you really have no exchange of anything going on there. So what about energy? Energy is the capacity to do work or to produce some type of change. And there's different types of energy that we come across. Uh, Energy is work done, and that's force times distance. There's chemical energies, for example, and that's energy that's stored within chemical units. So for example, in general, when we talk about energy and we talk about sort of this flow of energy, as we will see in this chapter for sure, there's kind of two types. There's a type of flow of energy which is known as being exothermic. And in an exothermic type of process, energy is released. There's also a endothermic process. And in an endothermic process, energy is absorbed. Now, when we talk about things in sort of chemical energy, there's actually energy, for example, stored in bonds. So if you have a bond between two things and you want to break it, do you think it takes energy to be put in to do that, or does energy need to be released to break a bond? Energy needs to be, what do you think? It does need to be put in. So that's an endothermic process. So if you have a bond like this, you put some energy in, everybody gains energy, and they just start wiggling away from each other. They got enough energy basically to break apart from each other. And opposite of that, if you want to actually make a bond, it is actually an exothermic process. So before you make a bond, everybody's got a lot of energy. So as they release energy, they kind of slow down and allows them to come together basically to make that bond without having too much energy that they want to kind of get away from each other. So as you kind of make a bond, they will actually release that energy in an exothermic process and allows them basically to make that pretty much bond. So that's an exothermic process, right? And this guy is an endothermic process. We see that kind of flow of energy right away in terms of exothermic and endothermic, just in like the ice cube sort of example, if you will, right? As we go from solid, which is say like an ice cube, you go to liquid. That is an endothermic process, right? You got to put heat and energy in there to do that. When you take an ice cube out of like the freezer, it just sits there, right? And it will start to melt spontaneously, right? And that's because it's picking up all the heat and energy from the surrounding air, and it will start to melt. And if you want to make some pasta at night, right, you boil up some water, some liquid water, it becomes gas, right? It goes into the gas phase, right? That's what happens when it boils. You see all the steam coming off. That's basically gas form of water. That's also endothermic. So phase changes as we go from solid to liquid to gas. Those are all endothermic processes. Those are all processes where energy has to be put into your system. In this example, water's our system, right? The ice cube gets the energy, liquid water gets the energy, right? So that's our system. The opposite is true if you're going the opposite way. If you're going from gas to liquid to solid, that's all an exothermic process. If you think about gas molecules, they're flying around really fast. You have a lot of energy. When they release that energy and they come in contact with each other, they now don't have enough energy to get away from each other. So they kind of clump together and go into the liquid phase. You continue to remove that energy, the liquid water molecules will come closer together because they no longer have more energy to do so, and they'll become ice basically into the solid phase. So endothermic processes as you go from solid to liquid to gas, exothermic as you go from gas to liquid to solid. And that's, again, that kind of flow of energy as we'll talk about. By the way, heat and energy flows from cold to hot or hot to cold. It goes from hot to cold. And that's why your ice cube melts when you take it out of the refrigerator or the freezer. Probably would be melted in the refrigerator. But if you take it out of the freezer, right, the ice cube is a much lower temperature than the room air, right? So the energy from the room air is hotter, flows from hot air to cold ice cube, right? Also why liquid water freezes when you put it in the freezer. When you put liquid water in the freezer, it's like room temperature, which is hotter, right, than the temperature of the air inside the freezer. All the heat and energy from that warm water is going to leave the ice cube tray, if you will, and enter the freezer air. That's going to cause the liquid water to freeze in your freezer, right? So all that energy leaves it, and then you have ice cubes, yes, if you have an old ice cube tray. We have also potential energy. Potential energy is the energy based on position. The classic example is, you know, the big giant boulder up on top of the hill that's going to fall over the top there. Based on its position, it has a certain amount of energy associated with it. It can then be transformed, for example, into kinetic energy, which is the energy of motion. So when it goes off the hill and falls, it gains some kinetic energy. And then when it hits the ground, it has a new potential energy as it hits the ground as well. Now, energy can be transformed from one form to the next. We do not lose or create energy along the way. So when we think about energy, which is the law of conservation of energy, this is actually like the first law of thermodynamics. Energy is not created or destroyed, but it can transform from one place to the next. So if we take our boulder example here, it has a certain amount of energy associated with it. As it moves, it gets and releases some kinetic energy. When it hits the ground, it will transfer that energy to the ground, right? Or hopefully nobody underneath it as well. But when it hits it, it will transfer that energy basically to the ground. So when we think about energy, especially in sort of chemistry, and we think about how energy is moving, oftentimes we think about energy as moving sort of perfectly, like there's a perfect sort of transfer of energy from one object to the next. So for example, if you were heating a beaker of water, the energy that that beaker is going to be releasing is the same amount of energy that like all the air will be picking up. Or if the air puts some energy into an object, there's like this perfect transfer of energy from the system to the surroundings or the surroundings to the system. So if somebody loses 5 kilojoules of energy, somebody else needs to gain 5 kilojoules of energy. So we don't lose anything along the way. It just moves from one spot to the next. Any questions on that there? All right, so thermodynamics, as I mentioned, is really the study of energy. And as you'll talk about when you go to 1B, thermodynamics is the study of really whether or not, for example, a reaction will take place or not under those conditions. There are certain things that are referred to as being state functions, and state functions are things that are not dependent on how you got there. There's only really kind of 2 things that are really important in terms of state functions, and that is where you begin and where you end, basically final and initial state. So if we look at these hikers, for example, they both started here. They both ended up here at the top of the mountain. In terms of their potential energy, they basically have the same potential energy at this point, even though they took different paths. The guy in blue took the more direct route. The guy in red took the scenic route around the mountain to get to the top. But really, in the end here, because potential energy is a state function, final minus initial, I guess energy there, not volume, is really the only 2 things that are important. And as you'll talk about, we'll talk a little bit about in this chapter, and you'll see it in 1A as well, and 1B to an extent. Sometimes people think, for example, all reactions occur in like one step. So sometimes people think like if I have A plus B, and it goes directly to E plus F. And that's not always the case. It may actually occur in multiple reactions. For example, you could have A plus B goes to C plus D, then C plus D goes to E plus F. And it can actually happen in kind of a multiple step reaction, 2, 3 steps along the way. By the way, you could add these together, and when you add equations together, anything on the left-hand side of the arrow and right-hand side of the arrow that are the same will actually cancel, like they subtract each other out. And then you can find out the overall reaction by just simply adding the left-hand side of the arrow, and anything on the right-hand side stays there, and that gives us our overall reaction that's taking place. So, for example, if there was a certain amount of energy to do this part of the reaction, there's a certain amount of energy to do the second reaction. You could find the energy to do this reaction by adding those guys together, these two guys together. The amount of energy required to do each of those steps would give you the overall energy to do the overall reaction. So that's the idea of state functions. There could be reactions that you look at an overall reaction, and maybe it takes 3 or 4 individual little reactions to occur for that to happen. You could actually add up, for example, the energy of each of those steps, and that'll give you the energy that's taking place of the overall reaction that's taking place. So energy, pressure, volume, temperature, these are all things that are state functions. And that's what we see here, by the way, when we see the delta symbol, that means a change. So that's the delta symbol, and that represents some type of change that's occurring. So when you have the change in energy, the change in pressure, the change in volume, the change in temperature, you can see really the only two things that are important is the final state and the initial state. That's also why, as we'll talk about, for example, in this chapter, when we look at a reaction, which, by the way, on the left-hand side of the arrow, those are what are referred to as reactants. On the right-hand side of the arrow, those are referred to as products. And our reactants are our starting material, and our products are pretty much what we get at the end. So a lot of ways that we could calculate, for example, the energy of a particular reaction is to take the energy of all the products that we made and subtract it from the energy of all the reactants we made. So again, kind of final state minus the initial state in a chemical reaction. And that's how you calculate a lot of energy sort of values, is you add up all the energy of your products in a reaction, which is where you end up, and you subtract it from all the energy of your reactants where you started from. And the difference will tell you whether or not, for example, a reaction is exothermic, giving off energy overall, or a reaction is endothermic, basically absorbing energy in that particular case. So that's a lot of ways that we calculate energy in these type of situations. Let's talk about some important units of energy and a couple of things that definitely you should know. So let's take a look at these here. The SI unit of energy is a Newton meter, and that's a kilogram meter squared second squared. These are not negative, it's just from PowerPoints, and none of these are negative on these. But this is a very common unit of energy. A joule or a kilojoule is two very common units of energy. Also, calories are kilocalories, and that is a lowercase calorie, by the way, with a lowercase c. There is a capital calorie with a capital C, that is a nutritional calorie, and one of the capital C, drawn dramatically there, is equal to 1,000 of the little calories, little c's, and that's 1 kilocalorie. So if you do see a calorie and it's actually capitalized with a C, it's actually a nutritional calorie, and that's different than a calorie with a lowercase c, which is sort of an energy unit. You should know that 1 joule is the same as a kilogram meter squared second squared. That is definitely a conversion that does pop up a lot. I will say maybe not too much in our class, but definitely in like 1A and 1B, they do pop up a lot, that conversion. So you should know it. You definitely should know this energy conversion here. That is definitely something that pops up a lot. 1 kilojoule is equal to 1,000 joules. By the way, 1 kilocalorie is equal to 1,000 calories. Again, this is the lowercase calorie. You should probably also know that as well. And the relationship between a calorie and a joule is something that you should know, which is 1 calorie is equal to 4.184 joules. The definition of a calorie itself is the amount of energy or heat that's required to raise 1 gram of water by 1 degree Celsius. This conversion down here that you should know, and this number is something that we'll see later on. This chapter is also a number that will pop up a lot in this chapter. 4.184 joules is something that pops up away. One way that we use energy is to change the temperature of a substance. And again, the temperature is not the same, for example, as, say, thermal energy. The temperature is a representation of the energy change. So when we talk about temperature changes, for example, if I have a really bad drawn thermometer here, my temperature goes down in this particular case, right? Did that substance gain energy or lose energy if the temperature goes down? Yeah, so for example, we just put numbers in, right? And we started, say, at 90 degrees Celsius, right? And it ended at 40 degrees Celsius, right? In this case, right, we can see the difference in temperature would be 40 degrees minus 90 degrees, right? The change in temperature. These were Celsius. And obviously here we would have like a negative 50, right? So it actually lost energy, right? So it would actually get colder, which means it will be losing energy in this case. Now, if the temperature went the other way and it went from 40 degrees Celsius to 90 degrees Celsius, in that case, that substance has gained energy, right? That's the only way we would see the temperature rise. And in the case of where it lost energy, this was a negative 50 degrees, right? And in this case, where it gained energy, we would take 90 minus 40, and that would be a positive 50 degrees. The amount of energy gained or lost in this situation is the same, right? The only difference is the sign, right? One's negative and one is positive, right? And typically when we speak about energy, if it is a exothermic process where energy is released, usually the energy value is a negative value. So usually when you calculate the energy value, you get a negative energy value for that. When you have an endothermic process where heat and energy is absorbed, you will end up with a positive value for the energy. And really the one thing that determines in most calculations whether or not, for example, you will sort of gain energy or lose energy is actually this, it's the temperature change, right? So again, based on the temperature change that you see, you'll either have somebody gaining energy or losing energy in this particular case. Any questions on that there? So thermal energy, as I mentioned before, is actually different than, say, temperature itself. Thermal energy deals with the amount of random motion of atoms there are in a molecule, and our molecule or a substance. So the more molecules or atoms you have, the more thermal energy you will actually have. And that may not be reflected, for example, in the temperature. So for example, if we had a cup of coffee at 70 degrees Celsius, and we had a bathtub of water at 40 degrees Celsius, it is the bathtub of water that actually has more thermal energy than the coffee cup there of coffee, obviously. And that's because in a bathtub, there is a lot more water molecules than there is, say, in a cup of coffee, right? There's a lot less water molecules in there. A lot more water molecules in the bathtub, a lot more thermal energy. But we do see a difference in temperature. And that is explained very simply, as we'll talk about in this chapter. In the coffee cup, it's a much smaller volume of substance, right? Which means it doesn't take as much energy to see a temperature change, right? So you need to put a little bit more energy in there to change the temperature of it. In a bathtub of water, there is a lot of water molecules, which means you need to take a lot of energy in there to see the temperature change just a little bit. So it takes a lot more energy because there's a lot more water molecules to get that to change. There's something we'll talk about in this chapter, which is known as specific heat capacity. And for example, for liquid water, the specific heat capacity, which is sometimes abbreviated S, is that number we just saw there, 4.184 joules per gram per degree Celsius. That means, for example, for every gram of water, and I want to raise the temperature by 1 degree Celsius, it takes 4.184 joules of energy to do so. Now, clearly in the bathtub, I have a lot more grams of water than I do in the coffee cup. And that means it's going to take a lot more energy to see the temperature actually change a lot, right? To get that bathtub water up to 70 degrees, you're going to have to put a lot of water in there, or a lot of heat and energy in there to get that kind of temperature change. In a cup of coffee, you don't. A more simple example is, right, if you took a big pot of water to make pasta, right? Does it boil instantly? No, it takes a while. You got to put a lot of heat and energy just to get it up there to enough temperature to get it to boil. If you put like a shot of water, right, in like a beaker, right, and you put it up there and on some fire, it's going to start boiling pretty quick, right? A lot less volume of water molecules that you need to change. So the higher specific heat capacity, it takes a lot more energy to change the temperature of a substance by 1 degree Celsius. So if you have a really big volume of water, like for example, the ocean, right? People are upset when the water volume or the temperature of the ocean, for example, goes up by like a half a degree or a very small amount. And you think to yourself, well, it's not a very big temperature change, right? The water, it didn't really go up by all that much. But you think about the volume of water there is in the ocean and the amount of energy needed just to move it up that much of a degree Celsius, that's a lot of energy to do that, right? And so that's why people get upset or worry about that, because even though it doesn't sound like it's moving a lot of degrees, the amount of energy needed to move that much water, just that little bit of temperature, is a lot of energy. And that's the idea behind sort of like the idea there, right, of global warming and all that type of stuff. But here again, in terms of the thermal energy, bathtub has more thermal energy than the cup of water because it contains more molecules. But in temperature-wise, we see the difference in temperature because it takes a lot more energy to heat up that big old tub of water versus a very small cup of coffee. Any questions on that there? All right, we'll lay it up there, I think, for today.